welcome again to the information session for the Building Technology program at the Massachusetts Institute of Technology. I'm thrilled to welcome you here. My name is Caitlin Mueller. I'm an associate professor at MIT in architecture, and I'm currently the director of the Building Technology program. Our agenda today is to share a little bit about our program, its history and its aims, tell you more about the specific degree programs that you might be interested in. We'll have brief talks by faculty about their current research and projects that they are interested in recruiting students to work with them on. And then we'll have a question and answer session with me and potentially some of the faculty on questions about the admissions process and how you can make your application as strong as possible. And then we'll have a final Q&A session with current graduate students that the faculty will leave for, so you'll have a chance to have a more in-depth conversation with students who are in a position you may be in the future. With that, I'm going to start sharing my screen and giving you just a little bit about the background of our program, and we'll have time for questions in a moment. All right. I assume you guys can see my screen here. So it's such a pleasure to welcome you to our community. The Building Technology program at MIT has a long and proud history of focusing on sustainability and environmental performance for buildings and structures across scales. We've been around since the mid-1980s, and the founder of our program is still a faculty member with us today, Leon Glicksman. In a few moments, we'll have him say a few words to give you more of his background. But today in 2025, we continue to be motivated by the climate crisis, our role within it, and how we as building scientists, building technologists, designers, engineers can contribute to a positive and sustainable future for buildings and construction. We focus across the spectrum from design, construction, operation, and assessment of buildings, and we have diverse backgrounds in a variety of technical disciplines. Some of us are coming from the structural engineering background, others are building physicists, mechanical engineers. We bring in technologies from social science, digital fabrication. So we're quite interdisciplinary, but we're united in this interest in harnessing advanced technologies to address some of the world's most pressing problems. We're also a really friendly and collaborative community. So this is a photo of our group a few months ago at the beginning of our fall semester at the MIT Sailing Pavilion. We find that our community and our collaboration is really critical to our success. So we have individual faculty members who run research groups within this program. You'll hear from many of us today, but we also are truly a family. We collaborate together on research. We have a strong social program, and we really find a lot of strength in our abilities to interact with each other and learn from each other. The faculty work very closely with students, with graduate students in these building technology degree programs. So we have 3 degree programs in particular that are focused on building technology: the Master of Science in Building Technology and the Master of Science in Architectural Studies in Building Technology. These are both 2-year degrees in which students come to MIT and develop original research, which culminates in a thesis under the close supervision and collaboration with one of the building technology faculty members. We also have a PhD program, which is a longer program that spans usually something like 4 or 5 years, in which students conduct more advanced research in depth, again, in close collaboration with a faculty supervisor. We aim for all of the programs to be fully funded, meaning that the tuition and stipend for graduate students is covered. That funding comes from a combination of sources. Sometimes that's faculty research, fellowship support, external funding, internal funding. So we have a very active research program in MIT Building Technology in all of our individual research labs where we are actively working on funded projects, and that's the primary way that students come into our program. For that reason, we have a strong lab culture. Most of the faculty members have organized research groups or labs in which our students are a member, and we direct research in this collaborative research lab model. We also have the Master of Architecture listed here. It's not one of the degree programs that we directly administer in building technology, but it is one that we are very involved with. So if some of you are here because you're interested in the MArch program, but you wanted to learn more about building technology, you're very welcome. Many of our faculty in building technology teach in the MArch program and contribute to it very actively in its curriculum. And we also work closely with many MArch students, both in independent studies, advanced elective courses, and in the thesis research that they conduct at the end. So I wanted to leave that here to make clear that we also are very connected to that program. I'll pause and ask Professor Leon Glicksman if you'd like to share anything more about the history and kind of future of building technology.
Thank you, Caitlin. Yes, I'd like to welcome you as well to this building technology breakout session. I'm a professor of building technology and mechanical engineering. And again, to emphasize what Caitlin said, the program is strongly focused on original research. And by that, we mean research, you're working with a particular one or more faculty members. During even the first term that you're here at MIT, we start you out on a research program. This is, again, a continuation of a program our faculty members are already working on. You're not going off on your own, but you're working closely with that faculty member as well as fellow students who are in the same research program. Again, as Caitlin said, we have strong ties to people in mechanical, civil, and electrical engineering, so we call on all the expertise throughout the School of Engineering as well as the School of Architecture and the work we've done. And then again, we are very close-knit community here, and we find that the students are very excited about the work that they're working on. So again, good luck, and we hope to see your applications.
Thank you, Leon. I'll just quickly say a little bit more about the backgrounds for the different programs. I've realized I mentioned them, but especially the first two programs, the second two, the two Master of Science programs are sometimes confusing for potential applicants, especially because they have very similar names. But they are intended to be different programs, primarily in the preparation and educational background of the students that are applying. So if you're interested in being involved in building technology as a graduate student, and you have a background in engineering or building science or building physics, and you're interested in learning more about how to apply that background in a research context in architecture, the Master of Science in Building Technology, the SMBT degree, is most appropriate for you. This is a degree for students who have primarily a technical background. If instead you have a background in architectural design, you have an undergraduate architecture degree, potentially you even have a professional architecture degree, the SMARCS Building Technology program is aimed at you. So this is a program that is aiming to bring people with architectural design experience into a building technology research environment, where we will teach you both the fundamentals of building technology, but also support you in developing your research skills and research agenda. Finally, how should you know if you should apply for the PhD program? The PhD program is intended for students who already have research experience. And that typically is evidenced through one or more peer-reviewed publication. So if you've already conducted research and published it in a peer-reviewed venue, like a conference or a journal, the PhD program might be appropriate for you. But often we find that students who are interested in our program don't yet have research experience, and so we often suggest coming in at the master's level. Many of our students who come into the master's programs do continue into the PhD, although it is a competitive process and you have to apply again to get into the PhD program. I'll stop here. If there's any urgent, immediate questions, I'm happy to answer them, but we'll also have a lot of time at the end of our session for more questions. With that, I'd like to turn it over to my colleague, Christoph Reinhardt, who is a professor in the Building Technology program, the former director of our program, and who leads the Sustainable Design Lab.
Thanks a lot, Caitlin. Welcome to all. Here we go. You see my screen? Everything's good? You should see a bunch of smiling people. I just want to echo what Caitlin and Leon already said, that We are a very close group. We do a lot of things together. We do some of the activities in our lab separately, and we welcome your application. And if you find that you are a good fit for our community. So the building, within the building technology program, as we said, there are several labs. I lead a lab that's called the Sustainable Design Lab. And the profile of the members of the lab is usually either a design or engineering background, but then a lot of the students also know design, computation, and programming very well. And increasingly, since the scope of our work has expanded from individual buildings to cities and now regions and whole countries, we are looking at policy experts as well to understand how the work that we are doing has maximum impact. And the regular kind of topic that combines us all is that we're working on workflows and planning tools and metrics that are used, as I will show, both in education all over the world as well as in practice to evaluate the performance of buildings, neighborhoods, and whole cities, and to basically improve decisions that are being made. And so to give you a little bit of a glimpse as well, I'm so glad that Caitlin also mentioned the MARC program. Teaching is really important for us. We basically bring the building technology technologists with the MARC students all together. And one of the underlying big topics is really that we want to teach evidence-based design. So we want to not constrain any design decisions that are being made, but we want to inform people what the implications of what they're doing will be. And then the hope is that a more informed design decision is a better design decision. And just to give you like a general sense how we are doing that, even in the first semester classes for the undergrads and the graduate students, when we talk about something like a shading study or solar radiation, we initially talk about really how do you predict where, with respect to your building, let's say the sun is located. How does this actually function all over the world? And then once we have this knowledge, we can apply it. For example, you see here a little graphic of Killian Court in the heart of MIT. So we can predict what would the shading be like in the space, what are outdoor comfort conditions in there. You can go a step further and basically explore then what the solar potential of all these different surfaces that you see are. So where would you place a window, or where would you put a PV system in place? And once you have this knowledge and understand how does it work, how can you apply it, then this translation into practice or into design decision really in the first semester culminates in the simulation game, where instead of a midterm, the graduate and undergraduate students compete. As you see on the left-hand side, they have 90 minutes, they have a budget, and who can design the most energy efficient building within 90 minutes to really give them a really clear sense what we are doing here is not just made for the classroom, but they should apply this throughout their career. And all of this with the help of several other universities, we've converted into this net zero buildings workflow pattern where we say this is a framework that you can apply for any building that you want to design, where you want to understand, is there net zero building potential? How do you look at both comfort condition as well as energy use in the building? And as we brought that out in the world about 12 years ago, we funded a company that has a plugin called Climate Studio for Rhinoceros 3D and now also for Revit, and it's used in practice and education everywhere. So for us, when you're in this program, you will see we have a direct line of the communication with these various firms to understand how they are operating right now. And of course, we want to share some of our knowledge and research that we are developing to see if that's relevant for them. Now, switching over to a large topic that we've done in the lab is this topic of urban analytics. And this started basically with solar mapping. So we developed this web app years ago where you can type in an address and you can predict the solar rooftop potential of your building. And that then got scaled and merged into, again, a commercial environment where people can look at their rooftops. Then it took us really 10 years to go from the roof of a building into the building. And here, this was really the combination of large urban data sets with building performance analytics, where we can take any city anywhere, use GIS data sets, predict building by building, or now even room by room, what the energy use or the indoor environmental conditions in the built environment are. And we just released this to see where this is finally going into somewhat like similar to akin to a Google for buildings. So if you type under mavi.mit your address, then you will see basically a cartoon section of the house that you're living in. If you are living in Massachusetts, you answer a few questions. We are predicting carbon emissions and energy use. And then we have this scenario developer that allows you to then predict or create a package of things, upgrades that you can do to your building. And in order to make this useful for policymakers, we basically then do research where we're trying to understand, are people actually willing to pay $50,000 to do an upgrade? So this was work by Zach Berzola, who's now the Building Decarbonization Section Head for the state of Maryland, where we used information provided by building owners in New England to do a regression model that based on a variety of parameters, their willingness to actually pay for an upgrade. And where this ultimately then leads is, if you're looking here at the city of Oshkosh, Wisconsin, we can break up the whole United States into areas where people going forward are very likely to retrofit their buildings in green, and those where this is not going to happen. And this is not to just say, oh, isn't that sad that some parts of the country won't upgrade? It's really to help focus policymakers where we should actually do changes. So this is a practical workshop that we did, series of 3 workshops in Everett. That's a low-income neighborhood or town in the greater Boston area, where Mariana Arcaya from Urban Planning, with whom we work closely together, had these 3 workshops where we helped low-income tenants how to advocate for themselves that they could upgrade the energy efficiency of their buildings as well. So this gave you some snapshot in what we're currently working on. Again, thank you so much for your interest, both in our program specifically, but in building science in general. Climate change is upon us. Buildings are really our line of defense during heat wave cold spells to keep humans healthy. So I deeply hope that you decide to pursue a career in this important field. If you have any specific questions for me, you can reach me at tito@mit.edu. And with that, I give it back to Caitlin. Thank you.
Thanks so much, Christoph. Our next speaker is Professor John Fernandez. John, are you ready?
Yes, I am, and I'm just about to share my slides.
Fantastic.
Hold on one second. Okay. So believe me, I've done this many, many times. There we go. 3rd time's the trick. Okay, so first of all, very good to be with you. I've got 10 minutes on, and I definitely don't want to go over time. I have a lot to show you. My name is John Fernandez. I am a professor in the building technology program. I'm also on sabbatical for this year. I'm returning in the fall, jointly designated with architecture and urbanism. I am on sabbatical now because I have been for 10 years running an environment center that has taken me far beyond the built environment, but the built environment is still really the core of the research that I do. So I thought it would be actually helpful to say a little bit about myself at the outset to give you a little bit of the trajectory of the work that I've done at MIT. I've been at MIT now for 26 years. So I came from industry. I'm a designer, I'm an architect, worked for a number of firms, have done my own work, continue to practice. When I came to MIT, the main focus of my work was in materials for sustainable buildings. So green materials, low embodied energy materials, low embodied carbon materials. And that eventually then led to another research thread that I started and have maintained for about 15 years now, working at the level of cities on resource flows, materials that are required, energy and materials that are required to run urban economies, not just buildings, but everything else. And I started the group called the Urban Metabolism Group. So that was essentially, the first half of, or the first 2/3 of what I did at MIT. 10 years ago, I took the position of director of the Environmental Solutions Initiative, which was MIT's largest environmental group on campus. And that took me deeply into climate. So my work went well beyond the built environment in climate and will continue to be focused on topics that are beyond the built environment in climate. but equally in biodiversity. So if you are aware of the latest climate science and especially the planetary boundaries, you will know that co-equal challenge, environmental challenge, is the loss of biodiversity. So some of the work is oriented on that. And by way of working with many students in computer science, AI is really very much at the core of the tools that we use for analysis and projection into the future. But again, I just want to return to the fact that I am at my core a designer. The building on the left is a net zero energy house that designed several years ago and built in the Hudson Valley. The building on the right is a large building in Hawaii. And I've been the author of many large buildings. And in fact, very recently, I've spent several years consulting for a developer here in Boston to build this skyscraper here on the right, which is now the commercial office portion of this building, is now the world's largest passive house office space. It's currently tracking at about 65 to 78% reduction of energy consumption below baseline EUI. I also am quite involved and will continue to be involved in different ways on the policy side. So I'm a member of the Embodied Carbon Intergovernmental Coordinating Council, designated by the governor of Massachusetts to develop the language, the pre-legislation language that will then lead to legislation that will bring embodied carbon regulations into the energy code in Boston and then the state. And I've also worked at the international level on topics like biodiversity and cities. I'm showing you this slide because these are the two primary collaborators that I've been working with for years and will continue working with for the foreseeable future for several years. They're both past researchers at the Environmental Solutions Initiative. Marcela Angel is a Master of City Planning from the Department of Urban Studies and Planning at MIT, and Norhan Bayoumi is a graduate of the BT program, PhD several years ago. The three of us work closely together. Each one of us has a designation of a topic. Marcela works very much on nature-based solutions, very often with communities. I work in cities, very often climate related. And Norhan works on AI, works with AI, along with the two of us on a variety of projects that we do. Okay, so let me tell you a little bit about the recent projects. On the nature side, urban biodiversity, we've been working in Latin America, primarily in Colombia now for about 10 years. We've worked in cities like Quibdó in the Pacific Northwest, Leticia in the far south, to bring tools and planning to communities to understand what is the biodiversity within and adjacent to their cities, and then how to enhance that biodiversity with co-benefits for the population, for the community. That led then to a nationwide program of biodiverse cities across Colombia, and we're working with all of them now on policies at using a variety of technologies and planning methods and community participation methods to address this issue of how to enhance biodiversity within and adjacent to the borders of the city. This is a sponsored project which is completed. EcoLens developed a data platform for biodiversity management within a city, collecting data on the ground using drones, citizen science, satellite imagery as well, to put together a mosaic of information to be able to establish what the biodiversity intensity within any urban zone is, and then working with the community on what are their priorities that are adjacent to enhancing biodiversity. Another project we did was a very particular situation in southern Colombia in a town called Mocoa, in which landslides have severe landslides had led to many hundreds of deaths over the past 10, 15 years. And using drones, machine learning to survey very large areas and to attribute the factors that most affect whether a landslide will happen or not to be able to produce a predictive model. And one of those factors happens to be the density of the planted material, so the density of the forests, the diversity of species adjacent to the town and on particular slopes overlooking the town. And the degradation of that biodiversity then leads to greater incidence of landslides. So that's one very particular project funded by the Global Environment Facility, which is a funding agency that normally funds large climate-related infrastructure projects. On cities, just going to show you 2 slides. We are about to launch online an online urban resource intensity tool that takes data for 11,000 cities and produces typologies of cities to be able to understand what's the range of urban resource intensity across the world, and then how do different cities apply policies to be able to become more sustainable. This slide I'm showing you just to say that I also am very keen and will continue to be involved in startups. So this is a startup, as Professor Reinhardt showed, you know, a startup, a company is one way in which to actually bring solutions to the world. And we need solutions today. So I'm very keen to work with students who may have this interest alongside, obviously, their degree. And this is a company that was started many years ago, and it deals with urban information. I don't have time to go into detail about it, but it was just recently bought by Gravity, just last month, actually, bought by Gravity, and bodes well for a more informed planning process, especially for large and contentious projects. Okay, and then on AI, just to show you a little bit of the work, we apply AI. I think I've already alluded to several projects in which we used AI, machine learning, and drones and other robotics to collect information. This is a particular project in the Bronx in which we did work to assess the enclosure performance, the building enclosure performance of low-income housing, to be able to advise a couple of community groups on what was the most effective retrofit actions to take. That work actually turned into a company called Lamar.ai. This is just an image of our latest platform that we've created for the company, and we provide this service to any owner or manager of buildings that want to understand in real detail the performance of their envelope. I have 7 seconds, but I'm going to take 15 or 20 seconds to say that an outlier body of work that we've been involved in, this is really just for fun, and this has not involved any building technology people, but I just thought you might want to know. We've actually gotten involved in understanding the emissions of the music industry. So we've been working with a couple of different players, including Coldplay and Above and Beyond. If some of you might know, that's an EDM group. And we've used our core expertise in building technology to analyze the types of venues where live music happens. And we've also used machine learning and a couple of other applied math strategies to be able to understand what is the largest emission source, and that is fan travel, the emissions related to fans traveling to a live music event. And we actually, just within the next couple of weeks, we are going to release a large report with Warner Music Group, Live Nation, and Coldplay on the total emissions attributable to live music in the US and the UK. And I thought I would just end here with this fun video of an event that we held on the MIT campus, where we were projecting climate images onto the Sana building, which was in construction at the time, as part of our interaction with the music industry. And one last thing to say there, working with the music industry means you're working with people with huge platforms to be able to communicate climate information. I'll leave it at that. Thank you so much. Back to you, Caitlin.
Thank you so much, John. Super exciting to see all this. Our next speaker is, I'm going to have to represent her because she's speaking at a conference in Mexico at the same time. But I'm so thrilled that she's with us in building technology. So I'm going to tell you a little bit about her work. Let me just get this Ready? So we recently hired 2 new faculty members in building technology. One is Holly Samuelson, who you will hear from shortly, who we are so thrilled to have joined us. And the second is Mariana Popescu, who is jointly hired between MIT Building Technology and the Design and Computation program within the Department of Architecture. Mariana's position is also very exciting because it is also joint with the MIT Schwarzman College of Computing, which is a relatively new initiative at MIT that aims to understand the potential and application of computing across all of MIT. So how can computing play a positive role in across all of our disciplinary areas of expertise? And in particular, for Mariana was hired to be in between architecture and the College of Computing. She comes to us from TU Delft, where she was previously an assistant professor, and her work focuses on large-scale applications of computational knitting for architectural structures. And this is a topic she first began working on as a PhD student at ETH Zurich, where she worked in the Block Research Group and has culminated so far in some really incredible large-scale structures and prototypes that she's built in high impact venues around the world. So her work really is looking across architecture and structures through the mechanisms of computational design and digital fabrication through this medium of computational knitting and textile work. So these are some examples of her projects. She's interested in the relationships between global architectural geometry and form and this rich heritage of structurally informed geometry, but also in that interplay between the global and the local. So how do new means of fabrication, in particular these knitting technologies, afford new opportunities to engage with local geometry, to control local material behavior, to tailor properties that propagate back up to the global scale. She's been investigating this in a variety of ways, in many cases through these large-scale experiments. So she has these computational design pipelines that she develops in her research that lead to the efficient generation of these structures that are automatically linked to her fabrication workflows, that are also linked to prediction and simulation technologies. And all of these enormous large-scale structures that she's been experimenting with are incredibly lightweight. So they're all small-scale textile pieces that come out in one piece from these large-scale CNC knitting machines. She has a new one at MIT that she's setting up right now, and she's actively recruiting people for her lab to participate in this research. So I'm sorry that she's not here to speak more beautifully about her work, but I think this is a really exciting opportunity to get involved in a brand new research area at MIT. I'll just speak very quickly about these 3 projects that she's featured here. This one is inspired by the work of Pierluigi Nervi, where these articulated ribs are situated within a larger scale efficient shell structure. Here she showcases the potential to do that entirely with knit formwork, where the ribs and the shell are both articulated in this lightweight material that will eventually get cast with concrete. She's also done large-scale installations with architects showing the sort of ephemeral potential of these materials, including recently at the Venice Biennale. This is a piece that she installed in the Arsenale that closes in a few weeks, if you have a chance to see it, that also integrates a sort of experiential design component with integrated lighting. I think I'll stop here to share Mariana's work, but she is actively recruiting new students. To work with Mariana, you can either apply in the building technology program or the computation program. So if you're interested in working with her in research, I recommend reaching out to her directly. Her contact information is on the architecture website. And she can give you more advice about her specific future research directions. With that, I'd like to turn it over to my next colleague who will be presenting. And I believe Holly Samuelson, are you the next speaker? Are you here? We may be ahead of schedule, in which case I can present my own work. Let me just check our schedule, one moment. Yes, I think we're a few minutes early for Holly, and I don't see her in this room, but Holly Samuelson is our other newest faculty member in building technology, and she's a really exciting new lab that I think she can share with you shortly. But in the meantime, since I finished Mariana's part early, I'll share a little bit more about my own research. Actually, first I'll share one other person who's also at a conference right now and can't join with us. I don't have slides for his work, but another really exciting faculty member in building technology who's been here for quite a long time is John Oxendorf. John has a background in structural mechanics and archaeology and brings an interest and expertise in historic assessment of structures to both the consideration of these structures contemporarily and also the design of new structures. He's done a lot of seminal work in the environmental assessment of structures from an embodied carbon perspective, and has also recently been doing a lot of work on circular design with reclaimed structural steel, including the sort of assessment of reclaimed steel for structural purposes and starting to work on markets for circularity in steel within the United States. John is also the founding director of the Morningside Academy for Design at MIT, where he works closely across the institute to bring a sort of interest in design from a sort of a range of perspectives, from the technical to the creative, to many students and programs across MIT. And through that program, he also brings a research interest in design education. So if you're interested in learning more about John's work, all of our work, you can find some information about it on the Building Technology website. John in particular, there's a recent talk that he gave featured on the bottom, so you can view his work there. I see that our next colleague, Holly, has joined us. Welcome, Holly. Are you able to give a short overview of your research interests and what your projects you're looking to work with students on, Holly?
Sure, I'd be happy to. Thank you so
Fantastic.
much. Thanks for the opportunity. Just sharing my slides. Great. Can you see them and hear me okay? Great, thanks for joining me. So my group is called the Livable Spaces Lab, and we investigate how thoughtful building design protects occupants and public health. And so this slide is showing a background of my own professional background. So I practiced and did consulting for the architecture and construction industry for about 10 years. And then I've been a full-time academic for about 12 years doing teaching and research. But I think this slide could also represent what my students go on to do after graduation. So they've gone on to practice, they've gone on to consulting, and they've gone on to academia as well. Like I said, one of the main focuses is on reducing emissions from heating, cooling, and lighting buildings, because emissions themselves, burning fossil fuels, are a public health crisis. So we try to address that through making better buildings. Here's an example. One thing that I am very excited and my students are very excited about is looking at building grid interaction. So there's a number of things that have evolved about our energy context. We've added more renewables, we're electrifying buildings. And I would argue that this kind of changes the context from which our rules of thumb, our building codes, our best practices were made. And in some cases, I think it should change our architectural design decisions. Like I think that we are getting windows wrong in cold climate residential buildings because of all of this changing context. And so my students are looking at issues like this and other issues related to energy in the evolving grid. We're also interested in anything to do with indoor environmental quality and health. So some of my students are looking at window views. We are looking into issues of indoor air quality. and especially looking at issues of indoor thermal resilience. So we are looking at this in the context of our own neighborhoods. So for example, looking at older adults and how they might be exposed to indoor heat in architecture today and how we might improve that. But some of my students have also been looking at this issue in other countries as well. So here's a project in Nepal where my students have went on after graduation to turn this into a real project and a real startup company developing rice husks into insulation for emergency shelters and other extreme weather and temperature events. In India, we've been looking at protecting occupants from hot ceilings, so testing and simulating solutions like a radiant barrier under the ceiling or cool roof coatings. Some of my students were testing here in Mongolia a design of their own, which was for temporary housing involving bags of sand that could be used as thermal mass to help mitigate the giant temperature swings that happen in that desert climate over the course of a day. So that's just an example of some of the health and energy related projects that we've been working on. And then here is our current Livable Spaces lab. And you can read through this if you want. The description here, Live Lab investigates how thoughtful building design protects occupant and public health by reducing energy-related emissions and enhancing indoor environmental quality. And we use computational and experimental methods. So we do a lot of simulation, but we also do real-world testing and human subject testing. The lab examines how decisions shape building energy performance and occupant experience towards a more livable built environment. Thank you. And I'm happy to take any questions.
Thank you so much, Holly.
My pleasure.
I think we'll have time for questions just in a few minutes if you can stick around. Does that sound okay?
Yeah, that's great. Let's see.
So I'll just do a quick presentation of some of my research, and then we'll have time for questions across all of these different research topics, more about our program in general, and then we'll invite the current students to come in, can share with you and answer any questions that they can. So just bear with me while I do one more slideshow here. So my own research group in the building technology program is called Digital Structures. Like many of the other research groups, this is a theme I think that you'll hear a lot. We're very interdisciplinary. So although my group is based in the Department of Architecture, I actually often work with students from across MIT. And that's a real benefit, not only of building technology, but of MIT in general. I think this has been a theme we've heard from a few of the other faculty already, but where MIT has a really flat kind of infrastructure in terms of programs, taking classes, meeting people and working with people in other departments. And that's, I think, a real key to allowing us to have a really flexible and innovative ecosystem that's also really collaborative. And I really appreciate that spirit and try to embrace it in my own work. I, like some of the other faculty, have a mixed background. I have a background in both architecture and structural engineering. And my work and my research group is really interested in how we can bring those two disciplines closer together to advance the best of what's possible in design. A lot of that is motivated by the climate crisis and trying to design buildings that are more intelligent with especially how they use materials, how they can be more efficient while also promoting designer agency and sort of broader goals of architecture. My group brings, as I said, brings together a lot of people with different backgrounds. So some have architecture backgrounds, some have engineering, some have computer science or math or mechanical engineering backgrounds. And we're all kind of united in this idea of trying to figure out the future of how we can design in a performance-oriented way. So these are sort of the principles that a lot of our projects respond to. So how do we design structures and buildings that are responsive to our environmental obligations as well as our economical obligations, affordability? How do we understand design in response to available resources rather than an infinite supply chain? How do we incorporate the designer's intent and authorship as well as the needs of the humans who will occupy our spaces in well-informed and innovative ways? And then finally, how do we account for emerging processes, new processes for construction like digital fabrication? How do we respond to that? And how does that change design? A lot of the ways we try to answer these questions are through the use of computational tools. I'd say our work is sort of in two different main areas. One is more fundamental and theoretical in terms of developing new algorithms and methods and workflows and tools to use computation to support design processes. A common theme across them is linking human-driven design with performance. And lately we've been doing a lot of work with artificial intelligence and machine learning to support that. And the other half of our work is applied to specific building systems or materials. I've done a lot of work with concrete that I won't show today, but you can find some information about it on our website. And I've also done a lot lately with thinking about circularity and developing algorithmic computational approaches to working with second use or reclaimed or salvaged materials, which kind of changes the whole process of how design works and is also highly impactful as a response to the climate crisis. I'll show this quickly. This is a kind of early project that I did when I was a graduate student in the PhD program at MIT in building technology. I developed this tool that I thought would help support a kind of design-driven approach for designing structures that also incorporates performance. It uses an interactive evolutionary algorithm to suggest new designs for structures, providing a numerical score that represents structural efficiency, but also allowing for a designer to have a form of interaction where new designs are suggested, not optimized, not providing a single solution, but opening up this design space and creating new ways for designers to find solutions to problems beyond the sort of typical analog methods. And I found these kinds of techniques to be really exciting in my own sort of way I thought about design, but also in our teaching, in the way that we think about the future of design and practice. We find that we can find really high performing designs that reflect the best designs of history, but also new ideas that we would never have found by hand. In our contemporary work, this is work from a recent PhD student from my group. We're kind of scaling up these ideas as we are able to do so with emerging computational workflows. So here we're starting to scale up the ideas of a design space to really large scale kind of building scale problems where we're looking across materials, across systems, across sections to approach modeling very realistic problems in the design space very quickly and with really high performance. So this is making use of recent developments like automatic differentiation, which really change the game in terms of what we can do bringing performance into design. We also pursue these techniques in much more abstract ways, inspired by artists and sculpture. This is a work by the artist Janet Eckelman at the MIT Museum that recently opened that was a result of a multi-year collaboration between her and my research group, where we were developing new software tools to support her design process, which is really challenging because the materials that she works with are flexible, soft materials whose shape must be found through physical simulation or modeling and cannot be imposed. And so we developed a software tool that helps connect the artistic intent with the ability to simulate equilibrium for complex structures. And we got to then show this tool in an interactive display in the MIT Museum. This is a screenshot from that. And this has been a really fruitful process because it's really opened up our kind of problem space of design tools and allowed us to apply it in a really high impact way with a really incredible artist. We also are interested in how machine learning generally kind of changes the design process. This is a project from 5 years ago now, where we started to think about how we could harness scale. So that's a common theme in a lot of our work. We have a lot of structures that, as they become more realistic, have so many variables, have so many ways that they can be designed, that the decision space is so vast. And so one of the ways we've been interested in harnessing machine learning is to think about how that could simplify the problem. So rather than adding more complexity, can we sort of learn a latent space of representation across really complex problems? And we were able to do that a few years ago using kind of the early emerging generative modeling tools. This is a variational autoencoder that learns a compressed design space of a complex structure. We here parameterized this roof structure by 36 different variables, almost impossible to visualize or understand as a human. But with this machine learning model, we find this reduced dimensionality, this latent space that we see here in this landscape that starts to find connectivity and continuity across really diverse designs. And so we're really interested in machine learning, again, not to replace or substitute humans, but to add another layer of legibility and to introduce more ways to understand these complex systems and problems, ultimately to lead to better and more interesting and novel solutions. We've been doing this lately through another means of trying to understand how we could bring human intent and legibility into complex design processes driven by structure. Here, we're starting to connect a goal that can be expressed semantically through text with a structural goal. This is a really simple problem where we have a kind of 2D model of a building, and we have this goal where we want it to look like a skeleton, and we also want it to carry load. And we find that with these emerging machine learning models, we can start to do that. We can start to blend these goals because they both work on the same representation, this pixel space. And it starts to be really interesting, and we can start to find new ways to think about ornament and function in an integrated way that like kind of changes the way that architecture and engineering are typically thought of as separate. This has been work that we're continuing to investigate, trying to build more complex and sophisticated understandings of sort of human expressions of goals and intent and aesthetics and response. So we're getting kind of more into theory and neuroscience to try to kind of advance this technique to bring the sort of human perspective into algorithmic processes. This is another example of recent work from a current PhD student who's finishing soon, kind of with another goal to use machine learning to enhance design by learning representations of diverse and complex structures so that we can start to find continuities and understand the space across design decisions. Sarah developed a technique called a neural implicit representation for buildings, which works to represent all possible building massings in a city with a single parametric representation that can be interpolated meaningfully across, which then allows us to learn new things about potential buildings that don't necessarily fall into an existing parametric model, but can really come from any idea that anyone comes up with, can get projected into a space that can then be improved in terms of performance or interpolated in terms of blending between goals. This is an example of this work that she recently showcased at the Venice Biennale, where she's showing how we can interpolate between really diverse concepts. And then she's using this representation that she's developed to also form the basis of a predictive model. So because of the shared representation that she's generated, she can then train a surrogate model across any possible geometry to get high fidelity prediction. In this case, she's predicting pressure coefficients on the building massing to bring kind of performance-driven design way earlier into a design process with very little upfront work. The final work I want to share is more on the second topic related to materials and applications, which comes from an interest that's developed organically at MIT in circularity over the last 10 years or so. We are inspired by images like this, which show traditional boat building techniques where the structure and form of the boat is directly informed by the material source it comes from, in this case, trees in a particular forest, whose specific branching geometry provides really strong structural connections for free and drive directly what the geometry of the ships that they will construct will be. It's very different from how we design today, where we assume infinite resources that can be manipulated in any possible way. But if we apply a similar logic to architectural structures, really exciting opportunities start to emerge, where these joints or these forks in trees, which are normally thought of as garbage or waste and are usually chipped, can turn into high-value structural connections. Here we're salvaging, that was this early version where we started this project, where we were salvaging tree forks from the chipper, where all the carbon stored in their fiber would get released into the atmosphere in a year or two, and instead consider them to be high-value structural connections, which we can bring into a digital twin modeling environment and start to allocate them algorithmically to a target design. How should that design change in response to the inventory? We've developed a lot of algorithms to support that process. How do modern fabrication techniques handle variation in the supply? We've had a lot of interest in in exploring how robotics can play a role. So all the path planning for debarking each individual tree fork can be automated, even though each fork is different, through a shared parametric logic. And then we can start to think of new types of kits of parts that are organic and varied, but still follow a kind of consistent logic and an ease of assembly. So it's kind of a new vocabulary that emerges for architectural design based on this idea of circularity, where we can start to reconcile available materials with form generation. We've been really interested in this topic, and many MIT students have loved working on tree forks, so we've done a lot more since then. This is a more recent project we did without a robot, where we used augmented reality instead to support handling irregular materials. We recently showcased this at an exhibit together with KVA and my colleague Sheila Kennedy at the Venice Biennale, where we imagined tree forks not only as structural connections, but the full gravity structural system of a building. This is part of the Odds and Mods program, which is a MArch Studio program with an accompanying workshop at MIT that many students in BT and outside of BT have engaged in. So if you're interested in this topic, there's a lot of activity around this at MIT right now. And we've been generalizing this technique to work on many different material systems that we use also in our teaching. So this is us teaching in the MArch program about how we can use algorithmic circularity to support material reuse. I think this may be my last slide. Let's see. Well, I'll stop here because it appears my computer has decided to stop working. But in general, this is we have a lot more work with reclaimed wood. So if you're interested in and this is an area I'm actively working in. So if you're interested in working with reclaimed materials for structural applications in an algorithmic way, that's a topic that I'm actively doing a lot of work in. I'll stop here so that we can have time for questions. Sorry, I'm trying to stop sharing. There we go.
I do have a question
Sure.
to Professor Holly. Hi,
Great.
my name is Jiwon, and thank you for your presentation. And I'm also interested in the occupant satisfaction and IEQ. So I believe my topics are pretty much aligned with your research. So first question that I want to ask is, for the public health and occupant satisfaction, I believe these metrics are not easy to predict, as many studies describe this as occupant uncertainty. So I was wondering how you measure an individual's subjective health and satisfaction in your research.
Oh, that's a great question, and you're absolutely right. So we've taken it at different levels. Sometimes we are taking the published literature, for example, on thermal comfort. But for example, we have a project right now where we are looking at older adults in housing and how they do or do not adapt to thermal extremes, and how we might come up with building interventions to help them. And in that case, we're asking surveys. They have wearables, so we're tracking their heart rate and their sleep. And then on that project, we're also partnering with my longtime collaborator, Amir Baniasati, who's an instructor at the medical school. And so in that case, we were testing things like grip strength, balance, gait, cognitive testing. We're asking questions about their mental well-being. And so we're asking, okay, are they hot? Are they hot and happy? Are they hot and healthy? And so we're looking at some objective ways that the temperatures and the indoor conditions might be affecting them.
So mostly you mainly use the self-reported data.
So for a lot of what we're doing, we're simulating indoor thermal conditions, and so that's our output. And so we're just looking at exactly like standard effective temperature, or some other metric of thermal comfort indoors. Yep.
Another question is, I was also wondering whether your work focuses more on mechanical systems or passive building systems to improve the public health and IEQ.
I would say I'm interested in architectural solutions, so more passive solutions. However, I'm definitely very interested in how mechanical systems interact. So for example, in a lot of what we're doing, I think it makes a big difference that we're switching from heating with fossil fuels to heating with heat pumps. And so I think that that has architectural ramifications. So that might be more on the energy side, but so we're definitely cognizant. So, I mean, sometimes we are, running through, different scenarios of heat pumps for that reason. But for the most part, it's to answer some question about the architecture. So should we, for example, have different windows or be doing something different with the insulation, that kind of thing. And we have another project where we're working with a new kind of indoor air quality sensor. And so in that case, we might be thinking about, well, how might we use this in buildings? So if we could better sense the indoor air, could we have much better demand controlled ventilation? And so that's one of the rare areas where, it might be more HVAC focused, but oftentimes we are focusing on passive solutions. Thanks.
Thank you.
And I'm sorry, I have to leave in about 5 minutes. Are there any other questions for me before I hop off? Apologies.
There is a question in the chat that is for Holly, unless if there's another specific question for Holly about her research, please do ask. But there's a general question about who is recruiting for which programs in the chat, which I can quickly answer, and then if any other faculty want to answer, they can. So we are all, all the faculty who gave presentations today are recruiting students. As I said at the beginning, our program aims to be fully funded, and that's often a very limiting factor in our admissions process. We often get more very well qualified students that we would love to have in our program than we are able to admit because of our limitations in funding. Although I think we're all doing a lot of work to try to raise money to support research, and so I would certainly anticipate that many of us are going to try to admit students. But we don't know exactly how many students we'll be able to admit because we don't yet know the full funding picture, and we haven't done the admissions process yet. Typically, we admit at least 2 students in the SMBT program and at least 2 students in the SMARCS program. Sometimes we admit more if we have more funding, and we typically admit at least 1 PhD student in building technology across all the faculty, and sometimes again more if we have more funding. I don't know if
I had a question
else.
for.
Oh, please go ahead.
Yeah, I had a question for Professor Holly before she left the meeting. Hi, thanks for your presentation. So if I understood correctly, is your research more focused towards indoor climate and livable spaces than towards energy efficiency? That's the first question. And the second question is, I heard a lot about AI in the research of the other professors as well. So is that something that you're also actively working with and trying to make use of in your research? Thank you.
Those are great questions. I think we're doing both. So we both have energy efficiency. And a lot of times maybe we're taking a new look at it that might be more health focused. So for example, kilowatt hours are not all created equal. So there are locations and times when using energy has much bigger health consequences. For example, maybe it's this inefficient natural gas peaker plant that needs to come on just for the hottest day of the year or something like that. And so in that case, we're thinking, well, if we redid the techno-economic analysis for architecture, maybe window shades are actually a great idea that are really cost effective because we're avoiding putting all this pollution in the air. So we are doing work with energy for sure, but also with indoor health and indoor environmental quality related to health. So we are using AI and machine learning. So we do a lot of data analysis. So in some cases, we're using machine learning techniques to make sense of all this data that we've either, gathered from the world or that we've created through our own simulations. And for example, working with Sherry, one of our SMARC students right now, she's very talented in AI. So she's diving into how we could use that to maybe interface with, this is kind of an idea that she hasn't started yet, but maybe to interface with these older adults to say how could we let them know when it's a good idea to take action and make it easy for them to take action and that kind of thing. So definitely open to new projects using AI and machine learning. Thanks.
Thank you.
Anything else before I hop off? Okay, so nice to meet you all, and you can find me easily on the MIT website. Thank you so much. Off to look for funding for more students. Bye-bye.
Any other questions?
Hi, I had a question. My name's Ryan, and so I've been doing like some research at Northeastern University in regards to computational design and building technology. And this question is a little bit directed to Professor Mueller. I am a MArch applicant, so I've been kind of listening to all the complex terminologies I've been thrown around in this meeting, so I feel a little bit out of place. But I was wondering, with the research that's been going on with all the professors around here, there seems to be a heavy kind of intense use of things of computational design, especially in like optimization and form finding. And so for MArch students that perhaps at most may have had, one or two research experiences that have kind of delved into those areas and would like to seek more in order to kind of contribute in a very efficient manner. Besides the kind of odds and mod studios and things like that, how can, let's say, a prospective MArch student kind of be able to jump into that?
Yeah, Ryan, that's a great question. All the faculty who have these research interests very often have a advanced elective that they teach for a diverse student population. So for example, I have a class called Computational Structural Design and Optimization, which is exactly intended for this purpose, to bring new students. It's actually quite diverse. It's undergrad, grad, many different departments into these methods in a intentional way with very carefully crafted assignments and project to help you learn the fundamentals. And I think that's true of most of the topics that we work on. We're really eager to bring them into the classroom. And in that particular case, many MArch students take that class. And so I think that's a very open opportunity.
Thank you.
And John Fernandez, I don't know if you have any thoughts on that since you're here, because you've also developed a lot of interesting classes connecting your research to students.
Well, I mean, Professor Mueller is exactly right. In fact, one of the classes I'm developing for when I come back in the fall will be a class on urban metabolism, which takes you through the core research we've done on the resource intensity of cities, if you're interested in that, and gets the students involved in research. The other thing that I just wanted to mention is that I've been teaching a class with Noran Bayumi the last few years on AI in the built environment. And two things I want to say. One is that that's also a kind of class that's available to anyone, including MArchs. We've actually had quite a few MArchs take that class. But the other thing is that you've heard a lot about AI, but maybe what you haven't heard is, for many of us, AI is not often the solution. It's just one of a number of tools. There's a lot of other applied math that is extraordinarily powerful. And often the first intuition to use AI is not the right one. You don't actually need AI for whatever you're looking at. So we take a very mature view of, and mostly what we're talking about is machine learning, right? So we do take an applied, robust, mature view of the use of these tools beyond the hype. Just wanted to mention that.
Fantastic. Any other questions?
Can I question?
Yeah.
Hello, Professor Mueller. I'm an architecture graduate from a 5-year BR program and have about 5 years of professional experience. I'm very interested in your research on structure design derived from natural generative principles, and I'd like to explore this as the main concept of my future design research. However, I only studied architecture engineer for a year before transferring to architecture BR program, so my structure knowledge is still developing, unmatured. So would you say it's still appropriate for someone with my background to apply to your program?
Yeah, thanks very much for the question. So if I understand it, you have a BArch and you're interested in whether that's a sufficient background for this program. And I think we absolutely take students with a BARC. We want to see some demonstrated interest and evidence of engagement with building technology ideas in your previous work. So we're not going to take people who have done 0 things in building technology and educate you from scratch. But if you have some evidence that you have been engaging in these ideas and have the aptitude and demonstrated interest to learn more, those are absolutely the types of students that we consider strongly in our application process.
Thank you for your answer.
Yeah, sure. Oh, sorry. Okay, one more question, then I'm going to shift to introducing our students. But yeah, go ahead.
Thanks. My name is Yuan Jia. Thanks for the introduction. I'm interested in learn with for working professional. I'm working in industry for 10 years and interested to pursue a more advanced degree in parallel. Would there be any part-time opportunity for pursue a PhD program?
Yeah, thanks a lot for the question. It's very atypical for us to have a part-time PhD students in the MIT program because we have a residency requirement and a full-time student requirement. So it's possible in some rare cases that after a period of full-time residency, you could continue, you could work in what we call an absentia. But I would strongly recommend, if you're considering one of our graduate programs at MIT, that you do not try to do that simultaneously while working professionally, because our graduate programs are intentionally very intense. We're really aiming to have a really strong, intense, educational process and also research engagement. And so we have found it's challenging to do that simultaneously while working. In other cases with students who have had a lot of professional background, some of them have been able to be very focused and complete, for example, the PhD program in a shorter period of time because they sort of know exactly what they want to do and are able to execute it quickly. So I think that's the more successful model that we've had with students from that background. I want to just give a quick, because there's a very good question about what we're looking for in the strong research statement. We do have our video from last year of this event where we also talk about that. So I'll give a very quick overview here, but then please, you can skip ahead to the YouTube video recording from our last year's open house where maybe we have more time, because I want to make sure you have time to ask questions to Sarah and Carl, who are current students. But in general, we are looking for a research statement that demonstrates your interest, knowledge, and motivation to work in a building technology area in your education and most importantly in your research. So usually that includes a little bit about your personal background. By that I mean your professional background. So what have you studied, why, what motivates you, what drives you, what experiences have led for you to decide to apply to this graduate program. What are the questions you're really animated by? What are the problems you want to tackle? Why are they important? And then a bit of a proposal of what you might want to work on specifically. The proposal is not binding. We're not going to force you to work on whatever you describe in the statement, but it's an opportunity for you to demonstrate your ability to articulate a research question, potentially engage in literature and context. So have you identified a problem that is unsolved? What are the closest works that have tried to address it? What are the remaining open questions? And then also identify how that connects with a faculty member's research interests. That's very important because the building technology program is, as I've said, a very close collaboration with faculty. So it's important to articulate a research interest that, yes, is specific to you and you should be authentically interested in it, but that also you have evidence that a faculty member is also interested. The ideal length through these statements is 2 or 3 pages maximum, so we're not looking for anything really long. We're really just looking to understand you and to have evidence and demonstration of your engagement in a timely and important and relevant research question. All right, I'm not going to have time to talk about the micro